This is the beginning of lecture notes 4, the introduction to ordinary least squares. So let's motivate this a bit. We've so far considered the relationship between two variables, but all we've looked at so far is correlation and covariance. How are y and x correlated with one another? This correlation might indicate two variables are related, but it provides no information about the structure of the relationship. Is it linear? Is it quadratic? Is it causal? We also can't control for anything. These last two are kind of the most important. Can we say anything about whether or not the variables are causally related? This is something that probably many of you have heard. Correlation does not imply causation. That's what we're trying to get at with regression the rest of this course. And we do that by controlling for things. We motivated this in the previous lectures with the analysis of education and wages, when we said that maybe ability was influencing education and wages, and that's a variable that's omitted from the analysis. So we want to control for things like ability. And this is what I call the real introduction to econometrics, when we start looking at regression. Oops. So let's introduce the population regression line. This is y equals beta 0 plus beta 1 x. These B-looking things, these are called betas. When we have the little tail here, it's a beta, not B. Beta 1 is the slope of the population regression line. Beta 1, if you know calculus, is equal to the derivative of y with respect to x. We would like to know the population value of beta 1 and beta 0, but of course we don't have data on the entire population, and so we need an estimator. Just like we didn't know the expected value or the population mean, we needed some estimator of it, and so we had the sample average. And now we're going to need an analog to that for a sample regression line. Here's the simple one regressor linear model. We hypothesize that the variable y is determined by another variable x, and we think the relationship is of the form yi equals beta 0 plus beta 1 xi plus ui. Notice that this is just y equals mx plus b plus an error term. So beta 0 is just the b in the equation for a line, and beta 1 is just the m, the slope. If we took out beta 0, it would just be correlation. Y is usually called the dependent variable. X is called the independent variable, the explanatory variable, or the regressor. And beta 0, again, is the intercept, and beta 1 is the slope coefficient. Here's some examples. We could say yi is soybean crop yield, and xi is fertilizer application. Yi could be crime rates and the number of police officers. And in the example in the book, it is yi is student-teacher ratio, and xi is test scores. And so we're going to relate these things going forward using regression. So a question, why do we have the subscript I on the variables? The variables being the y's and the x's, and in this case, the ui. The answer is we have a data set, and we're indexing each of the rows in our data set, or the observations, with the I. So if we had a spreadsheet with the yi and the xi in it, we could say the first row is equal to I equals 1, second row is I equal 2, third row is I equal 3, and so forth. And the data set might look something like this. y1 might be 3, x1 might be 4, y2 might be 2, x2 might be 5, y3 might be negative 3, x3 might be 1, and so forth. So we're just indexing our data set with these i's. They're not complicated. They're not a mystery. They're just indexing the data set. What about the ui? What about this error term? Why do we have that? Usually the relationship between y and x is not exact. If it were, we wouldn't need statistics. The assumption in most econometrics is that the ui is a random error term. You're going to need to know this going forward. The ui is a random error term that fills the imprecise gap between y and the right-hand side, beta 0 plus beta 1x. For example, if ui is equal to 0 for all I, for all rows in our data, then yi equals beta 0 plus beta 1x, which is exactly, we should have an I here, which is exactly the equation for a line, y equals mx plus b. However, we know that if we plot real data, we do not get a straight line. Usually we get a scatter plot. In economics and statistics, whenever we see straight lines or perfect correlation, we are suspicious. So if we plotted x against y and it looked like a perfectly straight line, we would be suspicious. This shouldn't be the case. We'd be able to fit a line perfectly there. Let's make this a little more concrete if we relate test scores to student-teacher ratio. So we have our regression line, yi equals beta 0 plus beta 1 xi plus ui. The regression line is defined by this here, beta 0 plus beta 1x. So that's defining the blue line. If we set x equal to 0, beta 0 is just going to be the intercept. So if we drew this, extended that to the y-axis, where this intersects the y-axis, that's beta 0. And the slope is just beta 1. This is negative in this case because it's downward sloping. The ui is going to be the, so if we took out the blue line, we would have a scatter plot, right? You just see the dots here. That's just a scatter plot of the relationship between test score and student-teacher ratio, y versus x. But then we plot these dots here, x1 and y1, as the first observation in our data set, and the difference between the estimated regression line and the actual points in our data are the error terms. So the difference between the first row in our data and the line is u1. The difference between the second row, x2 and y2 in our data, and the regression line is u2. We could keep going and say this is x3, y3. And that the difference between that observation and the regression line is just the third error, and so forth. And what regression is doing is it's taking this regression line and it's adjusting the slope and the intercept in such a way that it tries to minimize all of these error terms. It's minimizing the u1, the u2, and the u3. And we'll talk about how it's exactly doing it. But you can imagine if we took our pencil and put it on this regression line and we adjusted it so the slope goes up and down a little bit, regression is doing that adjustment. It's moving the pencil back and forth until those errors are minimized. It's trying to find the best line that fits this data. So how does this work? How do we get an estimator for this thing? How do we estimate beta 0 and beta 1 from the data? These are the population values. We want estimators of those population values. It turns out that we already know something that is a least squares estimator. What do I mean by least squares? Well, we're talking about ordinary least squares. That's what we call a regression line. Well, you'll see what least squares means in a second. Previously, we learned that y bar is blue. It turns out that y bar is also a least squares estimator of mu y, the population mean, expected value, y. Y bar solves the least squares problem. Minimize this expression, the sum of I equals 1 to n of yi minus m squared with respect to m. So y bar solves the problem of finding the value m, minimizing over m, that minimizes the average squared distances from each point in the data. So the distance, when we say distance, we're talking about the difference between yi and some value m, this bit here, the average squared distances. And so it's minimizing, if we're summing up over all the observations in our data set, it's minimizing all those distances squared. Y squared, well, if we didn't have it squared, then we would have distances that are both positive and negative, and we need to make them all, and so they would cancel each other out when we sum them up, and so we need to make them all positive, and squaring is one way to do that. We could also take the absolute value, but it's a lot harder to take a derivative with respect to an absolute value than it is a square. So let's take the derivative of that expression. You don't need to actually know how to do a derivative for this class. I hope that you've taken calculus, but you're not going to be asked to do this on a problem set or a test, but this is how it works. So minimization means taking the derivative. This function here, let me circle it, what I'm talking about. This function is going to be a quadratic function, and it's going to look something like this. And m is on the x-axis. F of m is on the y-axis. What we're doing is we're finding the minimum of this function right here. And the minimum is going to give us the best value for m. So let's, and to do that we take the derivative. Let's take the derivative with respect to m of the expression on the previous slide is this. The derivative of that is going to be, we're going to bring the 2 down. This is the chain rule. Bring the 2 down, and then inside, since it's with respect to m, and m is multiplied by -1, we're going to get -2 here. Then we're going to distribute the -2 in the sum into the yi and then -m, and we get the expression here. Then we're going to move the 2 sum yi to the other side, and then we have 2 sum yi equals 2nm, why 2nm? Because m is a constant, and then we're summing up m n times, and so we get an n here. We can divide both sides by 2 and multiply both sides by 1 over n. That just, if we're dividing by 2 and then multiplying by essentially 1 on both sides. So the 2's cancel out, and then we have 1 over n times the sum of yi right here, and 1 over n times nm over here. The n's are going to cancel out, we're just left with m. And then what is this expression here? 1 over n times the sum of I equals 1 to n of yi. That's just y bar. So this shows us that the best, the solution to the least squares problem presented on the previous slide, the solution m is y bar. So the best estimator of mu y, the population mean, is y bar. Y bar minimizes that function. Okay, OLS estimator predicted values and residuals. Suppose we have a sample of n observations I equals 1 to n from a population. OLS generates estimates of unknown parameters beta 0 and beta 1 in the population regression line beta 0, yi equals beta 0 plus beta 1x plus epsilon I. So we can, here I've defined the error as epsilon I, it could be ui as well. We write the estimates of the parameters with hats, beta 0 hat and beta 1 hat. So here we're going, this slide is taking us from the population parameters beta 0 and beta 1 to estimates of those population parameters beta 0 hat and beta 1 hat. So now we're getting a sample of data, just like we take a sample and estimate the sample average. Now we're getting a sample and estimating a sample regression line and getting estimates of beta 0 and beta 1. We denote those estimates with hats. We can predict the values of yi with our parameter estimates. OLS predicted values are denoted with hats as well. So we'll take those estimates of beta 0 hat and beta 1 hat and we'll plug them back into our regression equation, and then we can use them to get predictions or estimates of yi. What happened to the error term? This is a straight line through the data. There's no error term. So this is the definition of yi hat. So what are we talking about? So we have x and y here. The x1, y1 is going to look something like this. Here's our estimated regression line. Now we're actually defining the predicted values that are going to lie on those lines. So this is going to be y1 hat. So we're removing the error term u1 hat, and we're talking about the actual predicted values, the values of y that fall on this line, not the data points, but the values that fall on this line. We're going to go through this in more detail later on in this in this lesson. OLS residuals. So residuals are just estimates of the errors, and they're called UI hats. They're the difference between the sample values and the predicted values. So again, we have the YI, which are the data points, the observed data points, and the YI hats, which are the estimated or predicted Y's. I meant to put Y's from YI hat equals beta 0 hat plus beta 1 hat times XI. So we're taking our estimated values of beta 0 and beta 1 and then putting them back into the regression and getting estimates of the YI's, or predicted values. The residuals are just the difference between the observed data points and the predicted values. Okay, just like Y bar solved the minimization problem that we set up before, OLS also minimizes something. It minimizes the sum of squared residuals, the UI. So that's why we defined these residuals on the previous slide. OLS is minimizing the UI hat squared. It's minimizing over beta 0 and beta 1, and it's summing up over all observations in our data. We're going to plug in the definition of the UI hat over here. It's just the difference between the YI and the YI hats, and they're going to square it just like we did in the previous example, because we need these to be positive values. And then we can go even one step further and plug in the definition of YI hat, which is just beta 0 hat and beta 1 hat times XI. So the OLS estimator is minimizing the average squared difference between the actual values of YI and the predicted value YI hat based on the estimated line. So again, it's adjusting the slope and the intercept of the regression line until it minimizes those error terms, the residuals, the UI hats. The solution to the minimization problem, I'm not going to go through this in the lecture, but you can find how this is done both in the book and also in the appendix and the lecture notes. But the solution is given here. So beta 1 hat is equal to the covariance of x and y over the variance of x. And this is the sample covariance over the sample variance. We don't have to divide by the 1 over n or the 1 over n minus 1 because they would cancel out. In beta 0 hat, the intercept, we get that after we've estimated the slope just by plugging it back into this equation here, where we take the average of the y's minus beta 1 hat, which is estimated in the previous line here, times the average of the x's. And these are the averages over the y's and the x's in our data, the observed averages, the sample averages.